On one of our previous episodes, I think it was episode 22, we developed a method to transpose points onto a globe-like structure. When the globe is spun, it gives you the illusion of the points being laid out on a globe. It was truly a neat way to project three-dimensional points onto a two-dimensional surface, such as your monitor. The thing about this episode was that the globe was not interactive, meaning you can't spin the globe on your own, traditionally through mouse movements. So first things first, I want to correct that in this episode and then some more. Let's revisit how we project a three-dimensional point onto a two-dimensional screen. But first, let's look at what a 3D point is for a second. Starting with the 2D point, you already know what it is. It simply is a point on a graph or a screen representing the values on the two axes. This is what a representative class for a two-dimensional point looks like. A 3D point simply adds another dimension to this. Think of the z-axis or the z-axis that is inside of your screen. It's a way of saying how deep or how near is the point on the screen in addition to the x and y planes. Here's a representative class for the 3D point. So how do you project a three-dimensional point onto a monitor, which is essentially a two-dimensional plane? We'll use a technique called weak projection. Now, there are other techniques that are in fact the correct and better way to do this. These techniques use a variety of matrix mathematics and are a bit complex for me yet. For now, we'll stick with weak projection, but once I've mastered the complex mathematics, I'll pass it on to you. Alright, so a weak projection relies on the screen having a certain depth. Here is the formula to correct the projection and x and y locations from three-dimensional points. The values x projection and y projection are 2D points that will be drawn on the screen. Here is what the JavaScript code looks like. Note how the radius is calculated based on the value of z. Essentially, the deeper a point is on the screen, the smaller its radius must be. This will add to the illusion of that sphere or circle looking three-dimensional. So I took what we have seen until now and turned it into code. Here is what it looks like. A new set of points is generated every time I refresh the screen. These are just a bunch of randomly colored circles. These don't look like they have a depth to them, and the circles that are deeper in the screen only look smaller but without depth. So let's add code that puts a gradient to the colors of the circle. In JavaScript, the createRadialGradient function of the 2D context creates a radial gradient by using the size and coordinates of two circles. In this case, we are simply offsetting the gradient a little bit to the top left of the circle. Doing that makes the circle looks a little bit like a sphere. Here is what the randomly colored circles look like now. They can technically be called spheres since they look like they have a three-dimensional quality to them. No three-dimensional projection is complete without having the ability to move them around in 3 dimensions, or at least along the x and y axis. So let's look at that. Here is how you can move a three-dimensional point on an x or y axis. It really is that simple. I have a function over here called rotatex, which can take in an angle in radians. It calculates the sine and cos values of the radians using the math.sine and math.cos functions. The new x position is calculated as x into cos minus z into sine. The new z position is calculated as x into sine plus z into cos. And of course, the assignment to x happens over here. The rotation along the y-axis is exactly the same, except the y is calculated in exactly the same fashion as x. Here is the code that ties the dragging of the mouse across the canvas to rotation of the 3D points that are randomly spread across the screen. I calculate an x and y speed, which are basically differences between the current mouse location and where it started dragging, and then every point on the screen is rotated along the x and the y axis. And then I call a function called projection that ultimately projects it all onto a screen or onto the canvas. Let's see what that looks like. I've generated a random set of points, and when I move the mouse, you can see that it all moves in 3 dimensions. Okay, but what can we do with this? Let me introduce a couple of websites to you. This website is awesome. It's called ChemSpider and it allows you to search for a chemical or a molecule and download a three-dimensional representation in a file format called as a .mol file or .mol file. Let's see what the water molecule looks like. We all know that the chemical formula of water is H2O. I'll download the .mol file by clicking this button. Let me open this file in a text editor. Now I've opened the file in a text editor. It is a bit cryptic, but there is another format that is a better way to represent molecules in 3 dimensions. Let's look at that. It's called the XYZ format. XYZ files contain atomic coordinates. It generally has 3 things on it. The first line is the total number of atoms. The second line is the molecule name or a comment. Now the first and second lines are completely optional. All other lines is the element symbol or the atomic number, X, Y and Z coordinates separated by either spaces, tabs or commas. Here is what a representation of a file might look like. We are only interested in the atomic or the element definition and the XYZ locations. But how do I convert this mol file into an XYZ file? Here is another amazing website called OpenBabel. All you have to do is drop your .mol file onto this location over here. Select MOL file as the input format, select XYZ as your output format, and select 3D as the coordinates to be generated. And then you click on the convert. This will give you the XYZ files in this format. So let me just put that on text over here. I'll take these XYZ values and I'll convert them into a JavaScript object that will look like this. I took the XYZ values from OpenBabel and converted them into JavaScript objects that look like this. I have a bunch of molecule definitions. Over here, for example, I'm showing water and hydrogen peroxide, each with their own XYZ definitions. Each element that we parse has its own color. Carbon is gray, oxygen is red, hydrogen is cyan, and so on and so forth. The XYZ values are converted to 3D points by simply mapping the atomic positions to values between -30 and 30. You can of course change this as you see fit. Every element that comes through gets its own color. This is what the finished product looks like. This is water. You can easily identify it. It's H2O. Here is hydrogen peroxide. It's H2O2. This is ethane. I think this goes into your fuel or something. This is cyclohexane. This is Buckminster fullerene. And it's beautiful to look at. Here is benzene. This is a chemical called pyridine. It's exactly like benzene, but one of its bonds is actually replaced with nitrogen. That's its chemical formula basically. Here is methane. It's a very simple fuel, I guess. This is one carbon atom surrounded by 4 hydrogen atoms. Here is sulfuric acid. That's that one sulfur atom in between. In the middle, I'm sorry. Here is glucose. This is the glucose molecule. Here is sucralose. It's not sucrose, it's sucralose because it has 3 chlorine atoms. The ones that are in green are the chlorine atoms. Here is fructose. This is acetic acid. Now I'm not going to tell you what this is, but this is trinitrotoluene. Those who know what this is. Here is triamino trinitrobenzene. Those who know what this is, know what this is. Here is hyaluronic acid. I hope I pronounced that right. It has that one atom of sodium right over here. Alright, now since we have all of these 3D points, It should be possible to just sort of create words with it, right? And that's what I've done over here. This is the big int. We don't have to restrict ourselves to molecules. We can put our own text over here. We can create molecules that basically look like text, and we can have them animate. I've also added the double click event, which basically starts to automatically rotate all of these molecules. So let me just show the Buckminster fullerene again, and you can see that it auto rotates. And back again to big int. That's all I had to show for this episode. Thank you so much for joining, and thank you even more for subscribing. Goodbye.